In the beginning of this unit, we will start looking at probability, basic definitions, axioms. We build up all the necessary definitions in probability, representation, and then slowly we will go into probability distribution at the very end. So just go through the prerequisites that you need to know for this section. Pause and read through all the things you have to do. There are certain questions that will help you recap all the things that you should know about probability before we begin. So the lesson will be split into different sections. It's good to have a look back at these sections so you know where we're heading. So first we'll talk about set rules, and then from the set rules we'll build to set theory and specifically into probability. From this we will look at specific axioms, the addition rule, and mutually exclusive events. After that, we'll look at what complementary events are and some properties of the empty set. We will end the lesson with a few questions related to probability. So with set rules, you mainly need to know different notations. So one of the main notations is the union of two sets. So if I'm looking at A union B, I'm looking at either all the things that belong to A or to B. So this is an important word to use so that you know what this represents. Or in math also is represented by a plus sign. So if you have this event or that event, you need to add those two events together. Visually, if we look at a Venn diagram, what we typically do is we shade the area A, we shade the area B, and then the A union B is basically all the regions that you have shaded. So everything you've shaded is considered a union. On the other hand, we're looking at the intersection of two sets, A intersect B. So these are all the elements such that X belongs in A and belongs in B. And in math translates to a multiplication. So if we're looking at two things happening at the same time, you will have to multiply them together. Regarding what we do is we shade region A, we shade region B, and then the answer will be everything that has been shaded in common. So in this case, it would be the intersection here. So all the solutions here would represent the intersection of A and B. And you can extend this definition to more intersections, different intersections. There is a practice on how to shade different regions later on. Now building set theory notation just a bit more. U represents the sample space and it contains all the other sets. So it's this big space, everything is in there. Phi represents the empty set and A prime is the complement of event A. So everything that is not in A. So you would specifically look at A, and then everything that is not in that circle would be a complement. So because of that, we get the following properties. If A is a subset of U, we write it as such. So A is, you can think of it as under U. So A is inside of U. So if I take the union of A union B, so imagine shading everything in A and everything in U, that basically gives you the universal set. So the sample space is also called the universal set. If I take A union the empty set, again, I'm shading everything here, which just gives me A. If I take A and I shade with it everything not in A, I've basically taken everything into consideration and that would be the universal set. If I do intersections, if I take A intersect the universal set, so what do they have in common? They will only have A in common. A and the empty set, they don't have anything in common, so it would be the empty set. And A intersects A complement. Again, they don't have anything in common based on the definition, so the answer will be the empty set. So these are essential rules for probability theory. You don't have to memorize them, you can logically think through the solutions. These are some practice questions to help you know how to represent some regions. Things as complicated as, let's say, etch in here. So just to explain how you can go about that, look at each section separately. So it's like doing multiplication separately. So consider this region first, A union B, decide what the region is. Once you've shaded that region, consider that region and intersect it with C and look at the answer to this region. So always do it separately, and then you'll be able to figure out the regions. Be careful when the complement is on the inside and when it's on the outside. If it's on the outside, typically find the area that you're asked for on the inside and then just consider the opposite area when the complement is on the outside. So this is a useful exercise to do, and the solutions are on the next few slides. So now focusing on probability, now that we looked at set theory, just looking at the probability. The universal set in probability represents the collection of outcomes from a experiment. So everything that possibly happen. So for example, if you're rolling a dice, the sample space would be getting a 1, 2, 3, 4, 5, 6. And then N of U, the letter N represents you asking for, well, how many elements are in the set? And for the rolling the dice question, it would be 6, for example. So N of U would be 6. And then specifically, if we're not looking at a sample space, you might be looking at a specific event within the sample space. So for example, the probability of getting a 6 when you roll a dice. So that's a specific event, or the probability of getting an even number. So then N of A will be the number of ways A can occur. So if probability is, for example, rolling a 6, rolling a dice and getting a 6. So the number of ways this could occur is only one way. And the probability of it happening would be 1 out of the total number of ways it could happen. So this is the formal formula for it. Because the number of ways I could get a 6 is 1, and the number of elements in the set is 6. So in this question, it would be a 6 for rolling a dice. So probability of A would be N of A over N of U. And the probability of A prime is the probability of the event not occurring. We'll talk about complementary events later, but probability of not getting a 6 would be getting a 1, 2, 3, 4, and 5, which there are 5 ways of getting that out of 6 possible ways. So in probability, you already know this information, and probability gives you a number. It tells you how probable something is, and the answer is always from 0 to 1. If it's exactly 0, it means the event is impossible, and it has a 0 chance of happening. If it's 100%, it means it will certainly happen, and then all other probabilities would be in between. And if it's 0.5, then it's an equal amount of chance of happening or not happening. Now we will build on some axioms, corollaries, and theories. These are for probability. You already know these, you don't need to memorize them as certain axioms, but it's good to build up the definitions more formally. So for any event A, the probability of A is always bigger than or equal to 0. So this falls into here, that the probability of A has to be bigger than 0. And another axiom is that the probability of the universal set is exactly equal to 1. So the probability of everything happening is 1, certainly in total. So if I take the event of rolling a dice and then I look at the event of getting a 1, a 2, a 3, a 4, a 5, and a 6, it will give me 1. So I will certainly get one of those numbers. Now combining these two, because A is a subset of U, then since A has to be bigger than or equal to 0 and the universal set is 1, it means that the probability of A has to be between 0 and 1 inclusive. So this is what we talked about in the previous slide. The probabilities are between 0 and 1. So this is just the formal definition for it. So now we start getting to rules. We will look at the addition rule first. If I tell you P of A union B is equal to probability of A plus probability of B minus the probability of their intersection, what does that mean? So have a think through based on this Venn diagram. So the idea behind it is if I'm looking for the probability of A and B happening, so sorry, A or B happening. So it's either A happening, which this is part of A, and then if I'm looking at the probability of B happening, then it's, for example, the 6 here, and then the 5. And if I want the probability of A union B, if I look at the things I shaded, that would be 11, 5, and 6. So directly I can think, I can just add them together, assuming these are number of outcomes possible, and that would be 22 out of 24. However, if I directly just look at the probability of A, that would be 16 out of 24. And if I look at the probability of B, that would be 11 out of 24. And that will give me 27 out of 24, which is a bit of an issue because this probability is bigger than 1. So if I just directly take probability of A and the probability of B, why am I getting a bigger number than if I individually added them together? It's because I've double counted the intersection in there. So I've double counted this 5. So in general, if you need to look at the probability of A union B, and especially if they have an intersection, then you have to take the probability of A plus the probability of B, but you need to subtract the intersection because you already are counting the intersection in both of these. So you need to subtract a 5 over 24 to make sure you're not double counting the intersection. And that will give you the 22 out of 24. So this is called the addition rule, and it's a very useful rule. So you need to be aware of if you're looking at the union of two events, you need to make sure that you subtract the intersection. So this is in more detail. So if I'm looking at P of A, it's 16 over 24, P of B is 11 over 24, P of A and B is 5 over 24. So I need to take that away just once. On the other hand, we have mutually exclusive events. These are events that do not meet. So they're completely exclusive. For example, if you toss a coin, there's no way that you would get a head and a tail at the same time. So these are mutually exclusive events. You will not see them intersecting. So because there is no intersection, it means there's no double counting. So if you're looking at the probability of A union B, the addition rule then becomes P of A plus B of B, P of B only, because P of A intersect B would be equal to 0. So that would be the addition rule adjusted for mutually exclusive events. You can also say that if you know that the intersection is 0, you can assume that your events are mutually exclusive. So you can go forth and back with this rule. And let's build up to the third axiom now. We've already done axiom 1, 2, and corollary 1. Axiom 3 then says if you have a set of mutually exclusive events, so you can imagine in a full universal set, you have all of these are different events of A, for example, and you are taking the union of all of them, and they're all mutually exclusive, which means they have no intersection between them. Then the probability of A1 union A2 and so on is the same thing as taking the individual probabilities because you don't have to worry about the intersection. Now we go to complementary events. It was a bit obvious before that we talked about if you take the probability of A plus the probability of A complement, then it's equal to 1. We said because it's equal to the universal set if we go back to a few slides ago. This implies that if you're looking for the probability of the complement of an event, you just do 1 minus the probability of A. So a good exercise will be to try and prove this theorem using the axioms. So for example, when we did rolling the dice, we said the probability of rolling a 6 would be 1 over 6, which means the probability of not rolling a 6 would be 1 minus 1 over 6, which is just 5 over 6. We have further consequences of the rule. The probability of an empty set is 0, so there are 0 ways of it happening. And we talked about the probability of A being less than or equal to 1, but you can still prove them using the axioms, and the proofs are here. We'll go through two worked examples now, just to solidify the definitions and all the rules. So this is a basic example. You can pause, have a go through it about finding the probability of each event. These would be simple. I'll just lay out the answer. So you have a total of 11 possible options. So you have 11 in total here that you have to consider. And then if I need the probability of getting an A, I have two A's showing up in there, so it would be 2 over 11. For B, I have 4 vowels in there, so I have 4 over 11. For C, I have 1 C in there, so that would be 1 over 11. Now, for D, we're looking at OR, which means it's a union. So you need to rewrite it as the probability of getting an A or getting a C. So we're looking at probability of A union C. And they are mutually exclusive. The probability of getting an A and C, there's nothing linked between them. So if I look at the rule, I can just take probability of A plus the probability of C. So these would be mutually exclusive events. Which means it's just going to be 2 over 11 plus 1 over 11, which is 3 over 11. But in E, you just need to be a bit more careful because the probability of A or a vowel, we have a vowel. You have an intersection between them. You have the probability of A and the probability of a vowel, and then so probability of vowel, and then you need to take away the probability of A and a vowel, which means A is a vowel here. So that would be 2 over 11 plus 4 over 11 minus 4 over 11, minus the 2 over 11 again. 4 over 11 minus the intersection. So when do I have A and a vowel? That would be, there are 2 over 11. So that would just give me 4 over 11. So just being careful when there is an intersection. In this example, we're reflecting back on combinatorics. So we are looking at, there are 12 girls, 10 boys in a class, and you're picking students at random. So again, pause the video, try it out just to recap on definitions on combinatorics. In part A, they're asking for the different ways this can be selected. So they're looking at the number of possible ways this event can occur. That will help you find the total possibilities or the sample space. So in how many ways can the students be picked? You have 22 students in total, and you need to pick 2. The order does not matter, so you're doing combinatorics. You can do this manually or on a calculator. Manually would still be possible. So you go 2 factorial, 22 minus 2 factorial here. We will simplify the numerator to 20 factorial divided by 2 factorial times 20 factorial, so that these two cancel out. And then simplifying this will give you 231. So there are 231 ways of doing that. So when we go to part B, and they're asking for the probability that the students are selected, So you need to start calculating all the possible ways out of the total possible ways here. So the probability of selecting girls, again, the order does not matter, but the probability of selecting 2 girls would be 12 choose 2, which is 66. So the probability would be 66 out of 231. And then this would be I. And then if we're looking at both being boys, we're looking at 10 choose 2, which is 45. So it would be 45 out of 231. And then if we're looking at of each gender, again, order does not matter. If it did, then we have to consider different case scenarios, but it does not matter. So it's 12 choose 1 for picking one girl. And, so remember, and would be a multiplication, a 10 choose 1. So that would be 12 times 10, which is 120. So we get 120 out of 231. So that would be the answer to this probability. So have a go at the probability questions using basic axioms and rules, and then make sure that you familiarize yourself with all the rules and how to apply them.